Next, we're going to talk about fault tolerance. As I explained last time, a cluster or supercomputer has an enormous amount of concurrency. By having thousands or even millions of cores, it can execute a large number of things simultaneously and give us an enormous amount of power in order to carry out our science or engineering computing. But here's the problem. Anytime you have a complicated system, the probability of failure goes way up. And in a supercomputer with millions of components, failures of some kind are almost a constant presence. So we have to figure out how we're going to design our systems and our workloads so that we can accommodate the failures that are inevitable. Now, what sort of things can go wrong? There are many different sources of failure in a computer system. The most obvious kind, which you probably experienced yourself, is a basic hardware failure in one node of the computer. So that could be a power supply burning out. It could be a CPU that overheats and stops working. It could be a hard disk that's spun around one too many times and crashes and stops working completely. And if that's the case, then that single node stops working while the rest of the machine keeps going. We can also have software failures, and you've certainly experienced that as well. Operating systems can have bugs in them that cause them to freeze or crash. Applications can have bugs that get triggered under very rare conditions. It could be that the drivers for the hardware on the machine have bugs, and they crash occasionally. Now, the good news about software failures is that they're usually transient. When something goes wrong, the machine or the application will stop, and if we notice it, we can restart it again and get it going. What else can go wrong? Well, machines have a life cycle of all their own. When we install a cluster, it's the hottest new technology, but after 3 years, it may no longer be cost efficient to run and we have to turn it off. So in a large computing center that may have multiple clusters, in any given month we may be turning some machines on, we're turning some machines off, we're upgrading the operating system, and so things come and go over long periods of time. And from the perspective of the user, that can look like a failure because the machine is not available for a certain amount of time. In large systems, there are also social effects. So if you are using a big cluster, you're not the only person using it. There are multiple people coming in and trying to get access to the machine. And different people may have different priority. So you may be happily using the machine, but then someone with a larger priority comes in and your jobs get kicked off in favor of theirs because for whatever reason they're more important at that facility. From your perspective, that looks like a failure. We have operational errors. So as much as we would like our operators to be perfect, sooner or later somebody's going to press the wrong button or turn the wrong thing off at the wrong time. And so just through an accident of operation, a single machine or the whole thing can crash. And finally, there can be external events. Sooner or later, there's going to be a backhoe that digs into a power supply or a natural disaster that comes through and knocks out power to the facility. And that's a sort of failure that can take the whole thing offline. Those are the terrible things that can happen. Fortunately, they're rare. But if we have rare events for a large number of machines, the probability of failure can add up very quickly. So let me give you a very simple example. Suppose that you have one machine and it has a 1% probability of failing over the course of one day. That's probably a little high, but it works for an example. It also has a 99% chance of working successfully for one day. Now, suppose you had two of those machines, and each one has a 99% probability of working over the course of one day. What's the probability of those two machines experiencing at least one failure over the course of a day? Well, it's 99% times 99%, which works out to be 98.01%. So as we add machines, our probability of success goes down. If I have 10 machines, my probability of success is going to be 99 times 99 times 99 10 times, so that's 99 to the 10th power, and the probability of 10 machines working over the course of a day is 90%. Well, that's starting to get low enough that now we're getting worried about the probability of failure. And as our systems get even bigger, things get even worse. Now, we can compute the probability of failure for an arbitrary number of machines and an arbitrary number of failures by simply using the binomial theorem. So the coefficient for the binomial theorem is n choose k, p to the k, it's 1 minus p, that's the opposite of that probability, to the n minus k. And that's for n machines and k failures. And so here we've just worked out some example numbers for systems of various sizes with a certain number of failures. So as we saw before, for 10 nodes and k equals 0, the probability of success is 90%. And that seems reasonably high. If we are willing to tolerate at least one failure, then our probability goes up to 99.5%, that's good. And if we're willing to tolerate at least 3 failures, then it goes up to 99.99%. That sounds pretty good. But now as we go down this chart and increase the number of nodes, our probability of failure gets much worse. If we have 100 nodes and we want 0 failures, our probability is only 36.6%. If we have 1,000 nodes and want 0 failures, our probability is only 0.4%. And if we have 10,000 nodes, it's close to 0, as makes no difference. As you can see, for a sufficiently large system, we simply cannot guarantee that there will be no failures while you use it. We're going to have to figure out how to work around those failures. Now, there are also dynamic behaviors that can occur in a cluster when we consider all the users coming and going and the failures that can occur. So I'm going to give you a simple example of a day in the life of a cluster. So here, imagine each of these boxes to represent one node or one machine in a cluster. Now, initially the cluster is idle, and one user comes along and wants to use 18 nodes in the cluster, so they start running their programs on one portion of the cluster. We'll talk about exactly how that happens later. And then a second user comes along and takes a different chunk of the cluster, not necessarily the same number of machines, but now they're using different sets of machines and they're happy because they're not interfering with each other. Now, as I said before, bad things can happen. So suppose that one machine has a bad power supply that catches fire and the machine shuts down and it's no longer working. This is too bad for user 1 because they were depending on that machine, but it doesn't necessarily affect user number 2. Now, perhaps it takes a while to fix that machine, and in the meantime, a new user comes along and wants to use a different portion of the cluster. That's fine, but user 1 is still waiting to have that machine repaired. Suppose before we can get that one thing repaired, there's a power failure that takes out a whole rack of machines. This could potentially affect multiple users because there may be multiple users running on those machines. So now every user has been affected in some way. Now, we probably have some kind of scheduling system on the cluster that's going to notice those failures and try to accommodate. So having seen that some of these machines fail, it can take those users that needed some machines and reassign them to ones that aren't failing. So once we get reassigned, then at least some of the users are going to be happy that they got their original allocations. So in this case, user 1 and user 2 each got reassigned machines. Now, sooner or later, the system administrators are going to get out there and fix the machines. They're going to put out the fire on the one node and restore power to the one rack. And those machines will come back and join the system again. And now we sort of have a gap in the middle of idle machines. Now, if our users want to use some more, for example, user 3 wanted some extra machines, then perhaps user 3 can fill in those empty spaces and move their computation over to a larger number of machines. Now, as you can see, if this goes on for a while with users coming and going and failures and rescheduling happen, the system is going to get into a rather complicated state, and it's really hard to predict where it's going to be at any given point. It can be a very dynamic system. At any given moment in a cluster, you have to assume that something somewhere is failing, and the system and the users are going to have to accommodate that in some way. If you're a user of one of these systems and you insist on having exactly n machines in order to get your work done, it's likely you're going to be disappointed because some aspect of the system is going to get in your way. You might have n-1 machines, or to look at it another way, you might have n+1 machines. So the more flexible that you can be in the number of resources that you can use for your application, the more likely that you're going to be satisfied by the machines available in the system. Now, over time, the system can become fragmented. And this is a technical term that's used many places in computer science that means simply that all the like pieces are not together. Everything becomes scattered over time. So you can't assume that all of user 1's jobs are going to be in one place and all of user 2's jobs are going to be in another place. The dynamics of scheduling are simply going to cause them to be mixed up in quite a few different ways. And finally, while users and system administrators are always going to do their best to keep order in the system, a certain amount of change or churn is unavoidable. If you watch the status of any one of these clusters, things are constantly going on. Now let me show you a real example of the animation that I just showed you. Here's a display of the HT Condor system that we have here at Notre Dame from a few years back when we had about 5,000 cores in the system. And just like in the animation that I showed you here, each of these colors represents a job running on that cluster. The size of the square indicates the number of cores being used by that job. So whenever we have one little square, that's just a job using one core. And whenever we have a longer rectangle, that means a job that's using 4 or 6 or 8 cores. And you can even see way down here at the bottom, we have some that use 64 cores. Now the colors indicate the user who's running that job, and there's a key over on the left. And you can see at the moment we have 7 very busy users consuming anywhere from 123 to 1,465 cores. And as I just explained, this system is extremely fragmented. All the users are mixed up in different ways, and it's simply not the case that the users are blocked into one single place. Now here's something to think about. Which of these users is going to be best able to use the system? Turns out that the users that ask for a large number of cores are the hardest to schedule. Because in order to run those jobs, we have to find a large gap in the system where that rectangle can fit. But the users who submit a large number of small jobs are much easier to schedule because whenever one opening becomes available, we can put those users right in. So that's an example of how being flexible in the number of cores that you can consume allows you to get better service. That's an introduction to fault tolerance and its effects on clusters. In a cluster, failures are extremely common, so we have to be able to deal with them frequently. And we have to be able to design our system so that it's flexible to accommodate the dynamics of a changing system.